August 1961. Las Vegas, Nevada. A roulette wheel is an engineering argument. It is built to a single specification, that no measurement taken before the ball drops can meaningfully predict where it will land. The felt, the numbered pockets, the polished rotor, the ivory ball released at speed. All of it engineered toward one institutional guarantee. The house does not need to cheat. The house needs only the wheel to be unreadable. In the summer of 1961, that guarantee was wrong. Not in theory, not in a mathematician's notebook. Wrong on a casino floor in Las Vegas, where a device the size of a cigarette pack, hidden inside a shoe, was already transmitting signals through a wire to an earpiece. Signals that corresponded to specific sectors of a spinning wheel. Signals that carried a 44% expected edge. The casinos did not know. The physics had always been there. For decades, the casino industry's position on roulette rested on a single premise: that the gap between the ball's launch and its landing was too short, the variables too many, and the measurement too difficult for any observer to act on usefully. The wheel was not random in any strict physical sense. It was random enough. The industry had decided that random enough and random were operationally identical. Edward O. Thorpe, then a graduate student in mathematics in the mid-1950s, disagreed with the premise, not the physics. If you could measure two numbers, the ball's deceleration rate and the rotor's angular velocity at the moment of release, you could compute a probability distribution over the wheel's sectors before the ball fell. Not a certainty, a reproducible edge. The variables existed. The question was whether they could be read in time. This was not a gambling strategy. It was a physics problem stated in the language of measurement. Thorpe's position was that the industry had confused an instrumentation limit with a physical law, and that the distinction, once addressed with the right instrument, would not hold. Thorpe could frame the problem. He could not yet solve it alone. The solution required someone who understood both information theory and analog circuit design, someone whose thinking operated at the precise intersection of signal, noise, and physical measurement. He found that person at MIT. Claude Shannon had spent the previous decade constructing the mathematical framework that defined how information moves through systems. He was not a gambler. He was, by documented account, genuinely interested in the problem on its own terms. The challenge of encoding a physical measurement, transmitting it covertly, and recovering a useful signal at the betting moment. Between 1960 and 1961, working at MIT and in Shannon's own home laboratory, the two men designed and built a device using 12 transistors. It was analog, not digital, a distinction that mattered for the era and for the physics involved. The device was small, enough to be concealed, cigarette pack-sized, with its primary input mechanism mounted in a shoe. A toe switch allowed the operator to time the ball's revolution and the rotor's speed. The output arrived through a small earpiece, indicating which of the 8 sectors of the wheel had the highest probability of receiving the ball. In June 1961, they tested the device in Shannon's basement. The results were consistent with the theoretical model. A 44% expected edge on favored octant bets. Not guaranteed winnings, but a documented reproducible advantage over the house margin. The lab results were consistent. Whether a casino floor, with its ambient noise, its physical variation among wheels, and its surveillance, would produce the same level of consistency was a question the basement could not answer. In August 1961, Thorpe and Shannon brought the device to Las Vegas. The operational structure was straightforward. One person operated the toe switch to time the wheel and ball, transmitting the data through the concealed circuit. A second person received the earpiece signal and placed the bets. The communication between them was the device. No spoken coordination, no visible signal, no gesture that a surveillance floor could read. The tests proceeded at small stakes. This was deliberate. The purpose was not to extract maximum profit. The purpose was to confirm that the lab results held under real casino conditions: ambient noise, the physical variation between wheels, and the pressure of operating a concealed mechanism while standing at a public gaming table. The physics performed as the model predicted. Consistent with the expected edge, the device produced results that diverged from random chance in the direction the model forecast. And then the hardware began to fail. The specific points of failure were the wired connections, the links between the shoe-mounted input switches and the earpiece output. In laboratory conditions, those connections were stable. On a casino floor, with the physical movement involved in standing, shifting weight, and operating the switches through normal casino activity, the wires proved unreliable. Signal interruptions, connection losses at the earpiece. Thorpe would later describe these as the limiting factor. Not the physics, not the algorithm, not the casino's awareness, but the engineering constraint of building a miniaturized, body-worn, analog computer in 1961 with the materials and fabrication techniques then available. The tests ended, not because the device was detected, not because the method failed, because the hardware was not yet reliable enough to sustain extended operation at the level the method required. What the 1961 tests produced was not a fortune. They produced proof. After August 1961, the device went quiet. Thorpe did not publish the project. Shannon did not present it. Between 1962 and 1965, MIT's research community produced landmark work across computing, information theory, and signal processing. Fields, directly adjacent to what Thorpe and Shannon had built and tested. None of that output referenced the Roulette computer. The first wearable computer was advancing in history, silently, while the institutions best positioned to recognize it worked around it. Two conditions held the project back from disclosure. The hardware had not been fixed, and Nevada law had not yet explicitly addressed device-assisted advantage play. That prohibition would come later. Thorpe's 1966 account did not explain the 5-year gap. The reasons remain his. It was not until the second edition of Beat the Dealer, published in 1966, that Thorpe provided the first public account of the project. By then, 5 years had passed. The device was history, though almost no one yet recognized it as computing history. The casino industry's working assumption was precise. A roulette outcome, unreadable in real time by any human observer, is functionally random. Thorpe and Shannon did not challenge the physics of that claim. They challenged its engineering premise. The wheel's behavior was always deterministic, governed by deceleration rates and angular velocities that had been measurable in principle since Newton. What had never existed until 1961 was an instrument small enough, fast enough, and hidden enough to take those measurements at a casino table. The barrier was not theoretical. It was a fabrication problem. This distinction has consequences beyond the casino floor. Thorpe's subsequent career moved directly from roulette into financial markets, where he applied the same analytical framework. Identify a system assumed to be random, locate the measurable deterministic structure underneath, and build a method to extract a reproducible edge. The parallels were not incidental. They were explicit. What counts as random in any system is partly a function of what instruments exist to measure it. In 1961, Thorpe and Shannon built the instrument. The wheel had always been readable. What the 1961 device proved was not that the casino could be beaten. It proved that the casino's foundational guarantee that its wheel was a measurement problem no one could solve had always been an engineering claim, not a physical law. That distinction has not gone away. The original device is preserved at the MIT Museum. It is small, 12 transistors. Analog circuitry, a form factor designed to be hidden inside clothing and operated through a shoe. Built in 1960 and 1961 and field tested in Las Vegas in August of that year. It is recognized today as the world's first wearable computer, predating commercial wearable technology by decades. It was built not to advance computing. It was built to read a roulette wheel. The MIT Museum's designation came decades after the device was used. In 1961, Thorpe and Shannon had built a wearable computer. They had called it a roulette predictor.